Hey YouTube, it's Dimitri, and today we are going to talk about how to calculate gains tables here. So I'm not going to dive into a lot of the how to read gains tables or how to use gains tables or all that, but today I'm just going to go through these hand calculations inside of Excel. So everywhere I have worked, I have coded these out into whatever language we're using here. So I have coded them out in SAS so far, and I've coded them out in Python because that's what we've ended up using here. Now you could easily code them out into R or Julia or C++ or something else. But today we're just going to show you how to calculate these and kind of go through the mechanics of them in Excel, just because I think it's easier to see. And then I'll explain obviously why you should not be doing this in Excel and why it's better just to generate these in Python or SAS or R or some other language here. So first off here, to get a gains table, what we're trying to be looking at is we're going to look at how the scorecard, or kind of the model itself here, is going to rank order risk. That's what we care about. We want it to rank order. And rank ordering, as you'll see here, we can pull this up. If you look at a bad rate in this example here, you see that it's monotonic, so it's always every single decile. So we have 1 to 10 on the x-axis. These are the bad rates. Each bin gets worse. It's not necessarily linear, as you see here, because we have some wave in it, we have some curve, but every single point across the line, as it gets further down the x-axis here, so it's going towards the right, you see that the bad rate, so the y-axis, is higher and higher and higher here. So this is what we're looking for in a scorecard. This tells me that your model is working correctly, and it does not matter what your model is. So most banks are going to build out either logistic regression or GBM, so gradient boosting decision trees here. It's going to generate a probability of an event occurred here. So what we're predicting is going to be, we'll consider bads. You can define bads differently. It can be, default within 60 days past due, which we call 60 DPD. Within 90 days past due, 90 DPD or 120 DPD, or at the final state, which is just charge off. So you had a loan and it didn't pay and it literally charged off, meaning it defaulted here. It doesn't matter. You can set up models differently, which is another video and another discussion here. But we're modeling essentially either zeros or ones. So 0 is they didn't default, and 1 is going to be they defaulted here. And our model here, like logistic regression, is going to generate a probability between 0 and 1, which is the probability of default. So this model doesn't give us zeros and ones. You will have a score, which comes out of the model here. And as you'll see, these values are going to be random, essentially, in this made up data set here. But it's going to predict customers from 0 to 1, 0 probability of default to 1 probability. And then we're going to have an actuals column, which is the actual event that occurred. So they either didn't or did. So we're comparing the actuals here. The first thing you're going to want to do, so step 1, is going to be sort these by your score. So your model is going to have some sort of output. You need to sort them first. So in Excel, we would go through and sort them from smallest to largest. Again, you can use the sort function up here. I've already sorted mine, so you can see that we have the lowest being 0.01, so 1% chance of default, all the way down to 99% chance of default here. And you'll notice too, there's a few things I'm going to kind of point out just because I've made this a really small, simple example so you can understand what we're doing. We have 100 observations. And so when we do this, we're going to end up with some numbers that come out pretty nice and pretty, and I'll explain that. But when you have really, really large data sets, there's not going to be as clean of a cut here. But step 1 is going to be sort those scores. Step 2 is going to be we need to decile them. So this is why you would want to use Python or R or SAS or something like that, because what we want to do is we want to essentially assign these into a decile. So I mean, you can do this manually here in Excel here, but it should have, decile 1 for the first 10. And then you would have 2, which would be the second decile, and you'd go through this all the way to 10. And so you're going to have a column like this that has a decile number here from 1 to 10. Of course, 1 being the lowest, 10 being the highest here. We're just going to do it in that order because that's typically how I do them. Even inside of Python, for example, you would create a decile column and then you would do a group by here. So if we did the group by statement, we would group them. And what we're trying to look for is we're going to group all the deciles here by tens. For the bads here, you can just sum up the values because you have either 0 or 1 here. So if we sum up all the ones in the first decile, you'll see there's only one bad account here, and that sums over to here where we only have one bad account. Now you're going to have 2 bad accounts, 3 bad accounts. Now you're going to have to do an if statement, or you can just do what I do, which is I know there's 10 in each decile because I designed this, but in code wise, you don't want to do this because when you decile values in Python, for example, when you have a lot of records, often what happens is there's uneven amounts in each decile just because the number doesn't divide by 10 easily. And so you might have slightly more or slightly less in each decile, and that's okay as long as they're kind of close in general, especially if you have really large data sets. It's not critical if you have a handful of extra loans throughout. So the larger the data set, the larger the error can be in this. But the goods count is going to be the number of goods. So in that first decile here, we're going to have 9 accounts that are zeros here, meaning it's a good account. It did not charge off or default or whatnot. And so this whole piece here, the deciling, the goods, the bads count, that really needs to be done in some other language. I often go into Excel now after I generate all these and I hand check these sometimes because something doesn't look right in the table. And sometimes you can check your code. Like in Python, I create all this sort of stuff, or in SAS or whatnot. And you save it all up, but sometimes like things don't come out quite right. I copy my decile, my goods and bads in Excel, and then we're going to generate the rest of this by hand. Again, just do it all in Python and SAS if you can. The next column is going to be total. And so this is going to be the total number of observations in each decile. And as you expect, they should be fairly even. Now, the next thing that we like to do is calculate out the cumulative goods and the cumulative bads here. So let's do cumulative bads first. One thing is good practice is if you start with bads and do goods, every column ordering should be good, bads and goods, bads and goods, bads and goods. That's how it's done. In my other table here, you'll see I have goods and bads, but I keep that consistency across the tables. And so cumulative goods is just going to be all the bads summed up essentially, but just cumulatively across deciles. So the first decile is just going to be equal to itself here. So we have one bad. The second row is going to be the sum. We're going to sum the first and the second decile, which will be the cumulative number of bads here. I just put $signs around the first cell so that we can drag and drop. But if you look at the last cell, you can see this is going to be the total sum of all the bads, right? Cumulatively, once you hit the last bin, they should all be there. If you went back and looked at 9, for example, we're going to sum up all the bads up to that decile being 9. So as a note here, I call deciles bins often because credit uses these terms a lot and often they just get kind of interchanged. We're going to do the same thing for goods. And next we're going to create the bad rate. So this is one of the things that we're actually going to want to chart out and look at and review. So we have the bad rate here. And the bad rate is going to be the total number of bads divided by the total number of observations in that decile here. So we have 10% in our first decile. And we'll just copy and paste that down. I'll make a note, these don't have to be 1 at the end. This just happens to be all counts in this 10th bin are bad. So you can see from my very overly simplistic design here, I kind of designed them to rank just one after the other with exact separation, but this is not common in practice, which we'll look at here at the end example. Next, we're going to calculate out the cumulative bad rate. And to do this, we're going to do the sum of the bads for that decile here. So the sum of these bads divided by the total. So it'll be the same in the first bin. But now we're going to do the cumulative bads. So the first 2 deciles here divided by the sum of the total number of counts in both bins. And again, I'll go in here for simplicity. Put the $signs around there. I use F4 as the shortcut key. So F4 adds the $signs if you click on a cell in the equation here. And then I'll double click that. And as you'll see, if we pull up like number 8, it's going to be the total number of bads up through, so cumulatively through decile 8 divided by the total here. And that's going to give us our cumulative bad rate. Now the next 2 columns we're going to calculate, I typically call them cumulative bads percentage. This is just one way I've taught, but I've seen other people actually call this the capture rate. This would be the capture, bad rate. And so now this metric is a little bit different here. So I'm going to delete the capture bad rate here just because I think it's confusing. But we'll do cumulative goods percentage and cumulative bads percentage. And the way we do this now is that we're going to do the number of bads. We can just use cumulative bads, and we're going to divide that by the total number of bads now. So when we did, let's enter that real quick. And we're going to make this an F4. And I'll explain this here. So what we're doing is we're going to be taking the cumulative number of bads up to that decile and dividing it by the total number of bads. Well, decile 10 is cumulative of all deciles. So that's going to be the sum of all the bads here. So we're taking essentially the cumulative bads divided by the total bads. And this differs from the bad rate in the sense that when you do the bad rate, we're going across the rows. It's going to be the bads divided by the totals. So it's looking at the bad rates of each decile, which is what the bad rate is. The cumulative bads percentage here is going to be, as I mentioned, it's the number of bads captured out of all the bads here. This has to sum to 1 here. So when we drag and drop, these last two cells in our column should be 1. And if we do that, we get 1 here. So these are percentages. And we'll do the same thing for the goods here. So we're going to do the cumulative goods divided by, all the goods in summation, all the total here. And we're going to use the handle and drag and drop that. You'll notice that we have 100% on both. Now, you might be wondering, this rarely ever happens, that you see the same number, like 100% twice. The reason this is happening is just because if you look in the last decile, there are no more goods. So when we sum up deciles 1 through 9, we have 45 goods. When we add the last decile, there just happens to be no goods in that decile. And so we end up with 100% of the goods calculated in both of these two deciles here for the final calculation. Now, I'm going to plot these out real quick for you guys because this actually means something statistically. So this is going to be cumulative counts or cumulative percentages. This is going to be a CDF, so cumulative distribution function here. And these are going to be the percentages. And I'm going to set this chart here because the maximum difference between a decile, that's going to be our KS. So that is the separation, the maximum separation this model is getting from goods and bads. So we're going to take goods minus bads. And I'll note this because I've screwed this up and it doesn't really matter, but I'll explain this because we've had industry debates on this. Because I have structured my scorecard where 1 is the best, meaning there are more goods than bads, and 10 is the worst, meaning it has the most bads. When we do the KS calculation and we start from the top and go down, we're always going to start with goods minus bads here. Now, if you flip the scorecard over and again, your deciles were 1 to 10, but the more bads are on the top, and the lower ones in the bottom, your KS will just be negative for all the calculations. So it gives you the same value. I'll show you real quick. So if we just to prove this to you, if you did bads minus goods, right, you get negative 18 and positive 18. This is a common mistake, and then people start freaking out like there's no possible way, like the world's ending. No, it's just because you set your scorecard up a little differently. And so sometimes if I'm lazy and I set it up incorrectly, I try to recode everything, but if we're in a hurry for a model delivery or something, I'll just put an absolute value around it, which is not good practice. So don't do that. But what we're going to do is your KS, your maximum separation, which value here is the maximum. It's going to be 51. So that is your KS. Now I'm going to show you guys. So we're going to go to Google because Google is amazing. See if I can make this big. So here's an example just from Wikipedia, just to show you the cumulative probabilities, right? That is what we're looking at here, cumulative probabilities. And we're taking the maximum difference. Now you can have negatives and positives, as you can see here, like the blue line that they've modeled here goes above the red line. That gives you the separation. It's going to be inverse. So that's why you do not take the absolute value unless you can guarantee they're all positive or negative by checking the calcs and you're lazy. But please do the right thing and just correct that. It saves you a lot of time. But anyway, so that's what gives you the KS here for that chart, which is common in the space for credit scorecards, because I want to know if I can separate a lot of goods and bads. That's a good metric here. Now, to give you a more realistic example, again, completely made up here, what we're going to be looking at is we made a few made up tables with quite a few more observations. We did about 20,000 in each bin. And as you can see, it looks the same. We still have our, capture rate or our cumulative good percentages summing up that CDF to 1 in both curves. I plotted out, so just to kind of make a note on this as well, when you're developing models, you should have a gains table for your development data, and you should have a gains table for your out of time data. Now, you need to split your data into 2 parts to see if your model is even valid for a bunch of statistical testing reasons. But when we do this, what we can do is we can take a chart like this. And this chart, this bad rate, is plotting out the bad rate from the development and the bad rate from the out of time. And in most cases, you will see your development curve for bad rates sits below your out of time curve. This is because your model has never seen the out of time data. It's just scoring this data. So often we will build a model on, say, 10 years of data, 5 years of data, something like that. And then we'll save 6 months or a year or something, depending how many loans you have. And we will try to get a curve out of your out of time data of all these new loans that we've scored the model's never seen. This helps get us comfortable with the fact that, okay, the model is rank ordering our bads. So if it's in that decile 1, it's going to be the best loan that we originate here. And I know if I originate another loan, even just say in bin 3, which is slightly, a couple deciles away here with a different score, it's going to give us more or less another, a little bit of a lift. It's going to more or less guarantee that your bad rate's going to be rank ordering here. So you can kind of categorize interior loans in these categories. Now, something else I did not provide on here because I've overly simplified this. But often what you really want is you want to have your score here. And so I don't have it in here. So gains tables are absolutely amazing. So let me end with this a little bit here. You can add any sort of column you would like here. Any attribute that's in that data set that you have that you scored, you can add. So I work in auto finance, for example. Amount financed is something we look at. So somebody might ask, Dimitri, I think this model doesn't work. Say, okay, great. What do you don't think works on it? They say, this model is biased. Maybe it's overpricing really small, like low value loans. So like small amount finance. So maybe it's a loan that, you financed $1,000, $2,000, $5,000, and it's biased against, expensive loans like $35,000, $40,000, $50,000, $60,000 cars here. So you can use this gains table and use kind of the group by statement like in Python here, and you can come up with numbers here of the average amount financed for the bin. So it's going to take all this data, as we said before. It's going to have the amount financed, for example, and it's going to have some sort of dollar value, like, I don't know, $4,500. And it's going to have these values here within your deciles. And what's going to happen is you're taking the average of each decile, the groups, and those deciles are defined by the score, the model here, that logistic regression, that gradient boosting decision tree or whatnot. And so you should have averages here. And then again, you can plot these out across and see, maybe you have a pattern that's like, I don't know, convex, concave, maybe it's a nice even line. Like, you can help use this to make business decisioning on this as well. And back to this with the score, just to tell you how I do this. I typically put the average score here, I put the min score here, and I put the max score here. These will rank order because you've deciled by the score. So this is guaranteed in this sense. Now, your bad rates aren't guaranteed to rank order. If you had a bad model, it won't rank order. But it should be, from like 0 to whatever. So just to give you an example here, if we went back into our data and we averaged out that first decile, and we found the minimum value of the decile as well, and we found the maximum value, you'll see that you get, here, let me just add one more here. If you did all these, what you'll end up seeing is that your scores, so your average score will be the lowest in the first decile, and it will go all the way up to decile 10, which probably would average like around, 80 something points here, because the highest was 99%. You're gonna have something a little bit lower, something in there. But you can do that calculation and see the bins here. Now, when you do manual calculations, like you can do PSI calculations, which is population stability indexes, which I'm not gonna go over too much in here. You can do this for your development data. So if we had all these filled out, you can set up score ranges. So your probabilities here, your score range, and you would obviously set your score ranges, your first one to 0. So if you're going to do a PSI calculation, which I'll do another video on this because we're running out of time on this video, you would set obviously from 0 and you'd go up to your maximum score being 10842. Then when you'd set your second bin for this, your second score range, if you're actually using the scorecard here, you would say now the minimum for the next one is going to be the maximum from your last bin, because you don't want to have a gap. So you can see here, if you look at these, the difference between the maximum of the first bin and the minimum of the second bin is not the same. There are customers that don't fall in that range. So we have nobody that's, priced out at exactly 11%, because that falls between the bins here. Now, this would screw up all your calculations. It muddies the water in a lot of ways. The best way to do this is just to set up from 0 to the maximum scores all the way through. And then when you get to your maximum at the last value, you just do greater than that maximum from the tier before. So you capture all the way up to 1. Now you could hard code that if you wanted. That's something to look at. But these kind of help too, because you can kind of see the bandwidth of what percentages you're capturing in each decile, because you might not capture the same amount. You might capture exactly the same amount, but often some of the deciles, some of the bins will tend to capture a bit more on the score range here. So anyways, that's how you build a gains table. In another video, we will cover more or less how to kind of read these and get a little more insight from them. But thanks for watching. If you found this helpful, don't forget to like, share, and subscribe. And as always, until next time.